Hi everyone. So in our last video we introduced the concept of geodesics, and what that means is the shortest path between 2 points in your space. And we introduced them because it turns out they give us a handy way of finding the Christoffel symbols. So it's the third and easiest way of finding the Christoffel symbols. And so I've just reminded you here what the procedure is to find the Christoffel symbols this way. So you will have your expression for the line element in your coordinate system, and then what you do is find this Lagrangian. Okay, so Gij x dot I x dot j. In other words, this is ds by du squared. Okay, so if you have the expression for the line element, okay, so ds squared is Gij dxi dxj. To get this Lagrangian, basically what you do in practice is you take the expression for the line element, and where you have differentials, like here, dxi, dxj, you change them into x dots. Okay, so dxi becomes x dot I, dxj becomes x dot j. So you get this object called the Lagrangian, and then you plug it into the Euler-Lagrange equations. Okay, and this formula here you should know by heart. Okay, this is an important equation that appears in calculus of variations, in classical mechanics, lots of places in physics actually. So this you should know. Okay, so the curve that gives you the shortest distance between A and B will satisfy these equations. That comes from calculus of variations, and it's proved in the PDF notes online. So d by du of dl by dx dot k minus dl by dxk equals 0. And then when you put your Lagrangian in here and crank the handle a bit and just take these derivatives, eventually you will end up with equations in this form. Okay, so you'll have an x double dot term, and then you'll have some terms with pairs or products of x dots with something in front. And then whatever's in front, those are the Christoffel symbols. Okay, so that's how you can read them off. So I said we're going to illustrate this now by way of example. And we're going to go back to the case of a two-dimensional space described using elliptic coordinates. Okay, so a couple of videos ago I already showed how to find some Christoffel symbols in these coordinates using the formula with the metric tensor and the derivatives of the metric tensor. Okay, so that was the second method for finding Christoffel symbols. But now we're going to do it this way. Okay, and we shall hopefully see that this is the quickest way. Not always totally easy. Okay, there can still be some messy differentiation we have to do, but it's the quickest way to get all of the Christoffel symbols. Okay, so let's go for it. So I've given you once again the metric for these coordinates. So ds squared is equal to sine squared mu plus sine squared nu times d mu squared plus d nu squared. So the first thing we need to do is write down our Lagrangian. Okay, so the Lagrangian will just be L equals, and just do exactly what I said a moment ago. So to get the Lagrangian, just take your expression for ds squared, and where you have differentials, like here, d mu, just change it into a coordinate with a dot above it. So d mu just becomes mu dot, d nu just becomes nu dot. So this just becomes sine squared mu plus sine squared nu times mu dot squared plus nu dot squared. That's your Lagrangian. Okay, and now we go to the next step, which is the Euler-Lagrange equations. And because this is a two-dimensional space, two coordinates, there will be two Euler-Lagrange equations. So there will be an Euler-Lagrange equation for mu, and it will be like this. So d by du dl by d mu dot minus dl by d mu equals 0. And then the corresponding, so I'll just say EL, Euler-Lagrange equation for nu is d by du of dl by d nu dot minus dl by d nu equals 0. And by the way here, just remember what u is. U is a parameter for the geodesic. Okay, so you know, at the end of the day, if this is your geodesic between 2 points, and if you pick a particular point on the geodesic, it has coordinates xi. So in other words here, it'll have coordinates mu and nu, but they are functions of some parameter u. Okay, so in this case, mu is equal to mu of u, and nu is equal to nu of u. Okay, so the coordinates mu and nu are functions of the parameter u. Okay, so let's now get on to the hard part, which is taking this Lagrangian and putting it into these two equations. Okay, so here's our Lagrangian once again, and we're ready to go ahead and plug it into the Euler-Lagrange equation, first of all for mu, okay, and then we'll come to the other Euler-Lagrange equation for nu afterwards. Okay, so I think it's helpful here just to work out the various bits we need separately. So let's just start with this piece, so dl by d mu. And what will that be? So mu only appears here in the sine squared of mu. Okay, and by the way, mu and mu dot are independent variables. So whenever I take a derivative, a partial, with respect to mu, I treat mu dot as a constant. So when I take this derivative with respect to mu, I'm going to get 2 sine mu cos mu, okay, using my chain rule, and that'll still then be times mu dot squared plus nu dot squared. Oops. The square should be inside. Okay, so that's that part. And now I need this, so dl by d mu dot. And what will that be? Okay, if I differentiate with respect to mu dot here, well, this whole bit in front is constant then. So I differentiate this and I just get 2 mu dot. So I will just have 2 times this whole bracket. Sine squared mu plus sine squared nu times mu dot. So that's that part found. And then I have to take a total derivative with respect to u, so the parameter of the geodesic, of this thing that I've just found. So dl by d mu dot. So therefore, d by du of dl by d mu dot will be, so d by du of this. So we're going to have that factor of 2. And then we have to use product rule. Okay, so everything here is a function of u. Okay, so the coordinates mu and nu are functions of u, and mu dot is also a function of u. So product rule has to be used here. So I've got this bracket multiplied by this. So in the first term, of the product rule, let's keep this bit as it is and differentiate this. So we'll have 2 times sine squared mu plus sine squared nu, mu double dot. Okay, so it gets differentiated again with respect to u. And then in the second term, we will keep the mu dot. So we'll have that factor of 2 again, and we'll have the mu dot, let's put it here at the start, and then we differentiate this with respect to u. And to do that, I have to use the chain rule. So differentiate the first term with respect to u. How do I do that? Okay, how do I differentiate sine squared mu with respect to u? I differentiate it with respect to mu first, and then multiply the answer by d mu by du, which is just mu dot. Okay, so differentiate this, you get, with respect to mu, you get 2 sine mu cos mu, and then multiply by d mu by du, which is just mu dot. And then we also have to differentiate the second term with respect to u. So how do you do that? Differentiate it with respect to nu first, and then multiply by d nu by du, which is just nu dot. So that will just become 2 sine nu cos nu times nu dot. Okay, and now we can just put these pieces into the Euler-Lagrange equation. So it's just this thing, so d by du of dl by d mu dot, so this minus this equals 0. So let's take this thing, so that's going to be 2 sine squared mu plus sine squared nu times mu double dot, and let's do some multiplying out in this term as we go. So we have got in this first term 2 times 2 is 4, so we've got 4 sine mu cos mu mu dot squared. And then the second term, we've got 2 times 2 is 4 sine nu cos nu mu dot nu dot. So that's that term, and then so that's here, and then minus dl by d mu, which is here, so minus, let's multiply things out, so minus 2 sine mu cos mu mu dot squared, and then this bit as well, so minus another 2 sine mu cos mu u dot squared, and the Euler-Lagrange equations say that combination is equal to 0. And then let's try to see what we can do. So we can simplify, we can cancel some things out. So compare this term with this one. They both have mu dot squared times sine mu cos mu. It's 4 minus 2. Okay, so 4 minus 2 there will give you plus 2, so those terms will combine. And the others won't, okay, nothing else will cancel out. But I will do that, okay, and then also in the same step, I will divide through the entire equation by this thing, okay, the coefficient of mu double dot. So I shall say, therefore, when we do that, we will get just mu double dot, and then, okay, how much of mu dot squared do we have? So we're going to have 4 minus 2, which is 2. Sine mu cos mu from there, and then we divide by this, so divide by 2 gets rid of the 2, and divide by sine squared mu plus cos squared mu, so we will just have plus sine mu cos mu over sine squared mu plus cos squared mu times mu dot squared. Okay, hopefully I've done that right. What will the coefficient of mu dot nu dot be? Okay, so no cancellation with anything here, so it'll just be this divided by this. So we will have plus 4 over 2 is 2, so we're just going to have 2 sine nu cos nu divided by sine squared plus sine squared. Okay, sine squared mu plus sine squared nu times mu dot nu dot. I've just realised that what I've written there is total rubbish. So that shouldn't be cos squared nu, it should be sine squared nu. Don't know where I got that from. And then the last term is the nu dot squared. So that will have a minus, and we will just end up with that 2 will cancel that one, so we just have minus sine mu cos mu over sine squared mu plus sine squared mu. Times mu dot squared, and that's all equal to 0. And now remember the general form of the geodesic equation. Okay, so let me just put it here. So, general form of geodesic equation okay, which allows us to read off the Christoffel symbols. And remember, it was like this. So x double dot k plus gamma k I j times x dot I x dot j. That's a bit of a mess. Let me rub it out and fix it. And this equation is in this form. Okay, so this equation is in this form. So look, it's for the mu coordinate. Okay, so xk is just mu here. So you've got mu double dot plus something times mu dot mu dot. That's what this is. Okay, mu dot mu dot. So this is nothing other than gamma. And okay, so this is the Euler-Lagrange equation for mu coordinate. Okay, so xk is mu, so it's a mu upstairs. And then downstairs, this is the coefficient of mu dot times mu dot. So mu goes there. And this one down here is the same. So this is gamma mu. Okay, so it's the coefficient of mu. Now this one you just have to be careful about. So this Christoffel symbol, you might be tempted to think that this box that I've just done is gamma mu. Okay, but it's not. It's actually 2 times gamma mu. Okay, so this always happens for the mixed pairs. Okay, so it's okay for the mu dot squared and the nu dot squared, but for the mu dot and nu dot, this always happens. So the coefficient in front of it is actually twice that Christoffel symbol, gamma mu. Now, why is that? It's because of the symmetry. So remember that gamma mu is actually equal to gamma mu. Okay, remember, Christoffel symbols are symmetric in the lower index. And over here in this general formula, I and j are dummy indices, okay? They are summed over. So in principle, there's a sum over I and a sum over j, okay? So there will be a term here, in our case, where I is equal to mu and j is equal to nu. But there will then also be another term where it's the other way around. So I is equal to nu and j is equal to mu. And the coefficients of those two things get added together because this bit is just mu dot nu dot in both cases. Okay, so the two coefficients of the two separate terms get added. So really that's why you get this extra factor of 2 here. So the actual Christoffel symbol itself, so just gamma mu nu, will just be this thing without that factor of 2. Okay, so that's the Euler-Lagrange equation for the mu coordinate. And as you can see, this gives us a very reasonably quick way of reading off 3 of the Christoffel symbols. If you want it to, and I'm not going to do it here just for the sake of time, because this video was already long enough, but you could then find the Euler-Lagrange equation for the nu coordinate. Okay, so you will find d by du of dl by d nu dot minus dl by d nu equals 0. So you'll just find the derivatives in the same way and plug everything in, and you will get the geodesic equation for the nu coordinate. So you'll end up with a nu double dot here, and then some coefficients in front of these guys. And from there, you can read off the Christoffel symbols that have the nu in the upper index. I won't do it here because the steps are very much the same. Okay, so it's really line by line, it's nearly all the same. But I think now at this point we have seen enough maybe for me to try and give you a brief explanation of why we're interested in Christoffel symbols and geodesics. Okay, so I appreciate this still all feels very formal, very abstract, very theoretical. And let me just give you a 1-minute explanation of what the point is here. So When we finish this chapter, as we will soon, we're going to move on to general relativity. And it turns out, in general relativity, particles that are moving in a gravitational field, they follow geodesic paths in space-time. So that's why we're interested in being able to find geodesics. And as for the Christoffel symbols, why are we so interested in being able to find those? Why are we studying those so much? Because believe it or not, as kind of abstract and weird as they seem, Christoffel symbols are actually what keeps your feet on the ground. Literally. So if you're sitting in a chair right now, or you're standing, or wherever you are, the reason that you stay there and that you don't float off is because of Christoffel symbols. Okay, so in general relativity, non-zero Christoffel symbols are what give rise to the gravitational field. But we'll see that all in due course.